Okay, good. So, so where we are on Monday, we defined the notion of a cluster algebra, a fairly complicated notion combinatorially, invented by Fomin and Seliwinski now almost 25 years ago. And one of the main first results is that the cluster algebra is of finite type, has finitely many cluster variables, precisely when the quiver, which defines the cluster algebra, when this quiver is up to a mutation given by a Dynkin quiver. Yeah. And from very early on, this led people in representation theory to rush into that topic of cluster algebras because by all means, we do know Dynkin quivers. I mean, we know everything about Dynkin quivers. We know all the indecomposables. We know all the morphisms. So if there's a bijection between the indecomposable representations of a Dynkin quiver and the non-initial cluster variables, then by all means we should be able to understand the structure of a cluster algebra using representation theory. So there's the bijection non-initial cluster algebras versus indecomposable representations. But how do they form into groups? Yeah, a cluster algebra is given by a collection of clusters. So these are collections of cluster variables. So how can we interpret in terms of representation theory which of the indecomposables are joined together to form a cluster? Yeah, so that was the motivating question for many people understand that structure in terms of representation theory. Yeah. So um, in then I started yesterday uh, to illustrate that effort that has been done by many people in representation theory, and it is called categorification. So, is there a category whose behavior mimics sort of the combinatorial behavior in a cluster algebra? Yeah, and this category is then called the cluster category. So this will be the main goal and today to understand this cluster category. And I started yesterday outlining various constructions. One of the constructions is the construction of the derived category, which is a well-established but not so easy notion in representation theory. And I, in our case, where we have a Dynkin quiver, there's a theorem of Happel which shows us that the derived category can be constructed quite easily using this repetitive quiver. ZQ. So I will go quickly over this, and this also gives you the chance, if you like me to explain more certain things, you can ask me. We didn't have a discussion, so you can ask me if you want me to explain certain things in more detail. We can go over this again. Yeah. So we didn't have a real discussion yesterday, so please, if you want something to discuss, go ahead, ask the question, ask in the chat. We can uh, uh, discuss any point you wish to do. That's good? Okay. So we said we are given a Dynkin quiver Q. And then one thing we can do is define this repetitive quiver ZQ, which is just made of infinitely many copies of the original quiver. So ZQ would be given by infinitely many copies over that original quiver, indexed over the integers. And then I want to I want to these a priori disconnected components, I want to connect them, and I connect them by arrows in the opposite direction than the arrows in the original quiver. So like this, I can knit together these copies of the original quiver to obtain something that looks like a stripe, which is made of individual copies of my original quiver. So that's a fairly simple procedure, right? That's good. And also in this infinite stripe, we have the translation from one vertex to the next vertex on the left, which is called tau, and this remembers you of the Ausländerreiten translation. At this moment, this is just a translation on that quiver. Okay, tau moves one step to the left. That's all what it does. And then this is the result which I announced, the result of Hubble's that the derived category, which I didn't really introduce at this point, can be realized really using that combinatorial model in the case of a Düngen quiver. Yeah. So that's what we're gonna work on for now. And there's one more thing to observe that uh, generally the category of representations is contained in the category of in the derived category. So this is a full convex subquiver, the Ausländerreiten quiver of the representations. So inside that infinite stripe ZQ, we find some parts that are given by the actual modules or representations. So for our example, our basic example of type A3, quiver with three vertices, 1, 2, 3, we do know the module category, the representations are given by these 1, 2, 3, 4, 5, 6 objects. And this part embeds into that derived category ZQ in this way. And we can cover the derived category by iterated copies of that shape. Yeah. And when we do that, we introduce a notation, say this one is the copy 0, this is the copy 1, that one is the copy 2. So we do at the same time introduce something which is called a shift functor, uh, which is called a shift functor. And here's a formal definition of this shift functor. So when we have an object here, we started with the projective in 3. Then, so our knitting algorithm can be extended to the derived category just when we apply the knitting algorithm and we go past the module category, we have to pay a price for this, and this is that we accept negative numbers. This is what we discussed yesterday. But the additive, it's still additive on those vectors. Just those vectors do not represent any dimension anymore because it's negative. This makes no sense. But just we continue the combinatorics of those numbers. Yeah. Okay. So this formula allows us to compute the dimension vectors of the indecomposables recursively. So if we know tau m and if we know all the immediate successors, then we can compute the dimension vector of m because those are by recursion already computed. So this is the knitting algorithm. I can do it for representations. I can do it for objects in the derived category. So what I want to do now, so far this was a repetition, that's okay? So what I can do now is the following. I can also apply a similar knitting algorithm to compute cluster variables. So now this is new. Yeah, we compute, we apply the same algorithm uh, to the problem of computing cluster variables. So how would I how would I translate this? So assume we know some cluster variable at some corresponding to an indecomposable that corresponds to a module tau m, and assume we know the cluster variables of all direct successors of this tau m, assume they are already computed. Then what is the formula for the new cluster variable xm? This should be given similar to the formula that we had above here. Just the formula above is an additive formula, and we kind of have to translate this into a multiplicative notation. Yeah. So instead of subtracting the dimension of tau m, we divide by the variable corresponding to tau m. You see what we do? And instead of this sum here, we take a product over the xi, yeah? And in the computation of cluster variables, we always look at incoming and outcoming arrows. But since we proceed from left to right, there's only incoming arrows, so there's only this part, and the other part is empty. If the other part is empty, we write a 1. Yeah. So just we can use this formula to recursively compute cluster variables. Let's do this, okay? Good. Let's do that in our example. So here's the formula. Here's our example of the quiver, and let's start. So this is going to be very important to see what is going on. Okay, so I want you to be with me here. Um, we start with the initial cluster variables x1, x2, x3. They are there. They are given. Okay, and we arrange them in the way as the quiver is oriented. Good. And then we want to mutate the first variable. So the first mutation would, if these three are known, and I want to proceed like from left to right, then I would first focus on computing this one, x1 prime, yeah, because the this is tau of x1 prime. I do know the successor of that x1, then I can compute x1 prime using this formula. Good. So what is the formula telling me for x1 prime? For x1 prime, I would get, let me write this in red so you see where I am. So x1 prime would be a quotient of this form. I divide by the tau of x1 prime, so I divide by x1. Sorry, I divide by x1. And in the numerator, I write 1 plus the product of all variables that are the successors of x1, so 1 plus x2. This is what we get here. That's good? Okay. So we computed, so these are the initial ones. These are the initial variables. And then, so these three are the initial variables. Now we computed this one. So our next step of the calculation would be that variable, right? Yeah, for that variable, we know tau of that variable. We already computed all the direct successors, so we can compute this one. Yeah. What is the formula for x2 prime? The formula for x2 prime is we divide by x2 prime, we divide by tau of x2 prime, so we divide by x2. And then we have 1 plus the product of all the predecessors. These are these two, so we have 1 plus the product x3 times x2, no, sorry, x1 prime. That's the formula, right? However, we computed what is x1 prime already, so we go by recursion, but we can fill this in right now. So I replace x1 prime here by the expression which I already got. So this is 1 plus x2 over x1. And then if you simplify that expression, you would move x1 down to the denominator. So you find x1, x2 in the denominator, and upstairs you get, in the numerator, you get this expression. So this is x2 prime. Okay. And we continue going like this. So we computed this one. Next step, we would compute x1 double prime. X1 double prime, you can fill in the details. X1 double prime will be 1 plus x2 prime divided by x1 prime. And if you simplify, you get this expression. You can do the calculation yourself. That works out, okay? So we got x. Yeah.
I just think should be x1 plus x3 over x2.
Excuse me, where are you?
x1 double prime, it should
Yeah.
be x1 plus x3 over x2.
Did I make a mistake? Sorry. Did you do the calculation?
Yeah, yeah, and also by the
I,
symmetry, like 1 and 3 are
Sorry,
in.
sorry, sorry,
Yeah,
sorry, sorry.
yeah.
I
This looks
also have a
better.
question.
Yes.
So for X1, you looked at the successors of X1, right? In place of that pi of Xi. And for X2, you
Yeah.
looked at the predecessors. Why is that?
Um, if I compute this variable,
Yeah,
I divide by tau of the variable and I take 1
right.
plus the product of everybody that goes in.
Okay, and in place of like if you are computing X1, uh,
Yeah.
oh, okay, okay, fine, fine, fine.
Yeah.
Sorry, yeah, okay,
Uh,
fine.
now that the product of everybody that goes into x1 prime is the product of everybody that leaves tau of it, because I have this symmetry. Yeah.
May I
And
ask a question?
yeah,
So, so you said that this procedure will give you all the cluster variables. So, but is there any way
yes.
to say which cluster variables group together to form a cluster, or they are
E,
discrete information only?
this is what we really want to develop today. I'm working
Oh,
on this. So let's first
so
let's
sorry.
first compute all of them, and then we have to ask ourselves the question, so how are they grouped together? This is really the big question for today. That's good. Thank you very much. Yeah. So the let's assume we can continue with the calculation. We compute x3 prime, we compute x2 double prime. The results are here. Hopefully they are correct, Isha. And and we compute x1 triple prime. So I have hopefully in a correct way given you all of those. Okay. And so these are the initial variables. Then we find one variable for each place that looks kind of like the category of representations. Yeah. And then we need to continue. Yeah. I mean, I continue that process until I cannot continue anymore, or until I observe something happening. Okay. We need to continue. A priori, nobody told me here at this moment that I need to stop. Yeah. So assume we have computed all of this and we continue our process. Good. So the next variable that we want to compute is that first question mark here. Yes, that's good. So can you help me computing that one? Apply, can we apply the formula to this one? So the first question mark is here, and the first question mark will be given by a quotient of, you can help me, I divide by x3 prime, because that is tau of this one, right? Correct. And in the numerator, I'm gonna have to write 1 plus the product of everybody who goes in, and this is x2 double prime, correct? Okay, and then I need to evaluate that thing. So x3 prime was that big chunk. Okay, there's not much I can do. This is x1 plus x1 2 plus x3 plus x2 x3 over x1 x2 x3. And what do I have in the numerator? 1 plus x2 prime, x2 double prime. X2 double prime was the part, I just copied this part down here, right? So let me do that. So this one goes right here. That's perfect. Okay, good. So we have to, hopefully we can simplify that expression. I can cancel out the x2s here. I can cancel out the x3s here. Yeah. And what do I get? I bring the thing here on a common denominator upstairs. So there was 1 plus. So let me bring this onto a common denominator. I do some painful calculations here with you. Hopefully I don't mess it up. So 1 plus common denominator, which creates x2, x3 plus. That's okay? Okay. And then if we compare what do I have here and what do I have here? This is hopefully the same. Is it the same? Okay, good. This was the check if I make a mistake, yes or no. So this is the same. It is the same. What means I can cancel this out, and what is left?
X1.
X1.
An x1 is left. There's a 1 over x1 is left. So this is x1 here. I computed x1. You see that? Okay, perfect. So I hope you are convinced this actually works. I can leave you as an exercise, but what you really get here in the second question mark is that you get here x2, and what we obtain in the third question mark is x3. So what do we observe? You see that? This is the honest, true calculation of the we apply the knitting algorithm to cluster variables, and we obtain this picture. So this is very important. This is very important. So what we obtained, what we got as a result is the following. We have the initial variables. We do find the non-initial cluster variables, one for each indecomposable representation. And we do see that the indecomposable representations, they are like indexed by their dimension vector, and we do find an x1 here. We do find x2, x3, x2, x3, x1, x2, x3. So we find the dimension vectors of the indecomposable representations as exponents in the denominator. And the important thing is, besides the initial cluster variables and all the non-initial cluster variables, if we just continue the knitting procedure, we fall back to the initial cluster variables. So in that whole picture, we want to identify these two parts. Yeah, these are the same. Good. So that's the... Okay, so this is what I said, that as we know that the non-initial cluster variables, if I write them as a Laurent polynomial, so I can read off in the denominator the exponents which describe the sum of the simple roots. So this gives me bijection between indecomposables and non-initial cluster variables. But the important thing is I want to identify these two parts. This is what we learned. Okay. And this is our main idea. And how can we define the cluster category? We start with computing this derived category, but then we have to do some identification. I want to identify this part with that part. Yeah, I have the module category here in the middle, but what is left and what is then immediately to the right of the module category, I want to identify these two parts. And how can I identify? So let's start. Here's a module, the projective in 3. If I go with the tau shift to the left, then I do find tau P3 here. And how do I get this one? This is the shift. This is P3 shift 1. Now, if I want to identify this part with that part, that should mean these two guys need to be identified. I want to glue these two, those two, and these two. They should be identified. So what do I want to identify? I want to identify tau P3 with P3 shift 1. Yeah. So this is now my definition of the cluster category. Definition. Say we have an acyclic quiver, and by the way, this works generally not only for Dynkin quiver, so this is now the general definition of a cluster algebra for for a quiver that has no oriented cycles. Then the cluster category CQ is defined as the quotient of the derived category DQ by the operation identify tau with the shift. I just mod out this relation. Yeah, I mean, this is what I observed. I want that tau P3 equals P3 shift 1. So I just glue these two, I identify these two, so I take a quotient of that category by demanding that tau and shift coincide. Yeah, so that's the most important part for today. This gives me the idea how can we define the cluster category. That's okay? Good. So in our example, this is exactly what we observed. The cluster category would be given by the module category, sorry, by the module category, by the representations, and then on the right-hand side, we have the shifts of the projectives. On the left-hand side, we have tau of the projectives, but we said tau equals shift 1, so I can label them P31, P31. This is the same object now. Okay, so this is the cluster category. There's no really good way. Okay, there is a good way how to draw the cluster category. If I would take this piece of paper, I cut it out, and then I fold it and I glue this to that, yeah. But I would need to glue it kind of, I reverse it. I create kind of a Möbius band, you know what I mean? I mean, I would glue this one to here in that direction. So I twist it. So I would create something like a Möbius band, and I have a hard time drawing this. Yeah, so it is much easier for me to draw it like this, and I tell you, please identify these two parts in that way. That's okay? Because otherwise that would be I don't know. Can you draw a Möbius band? It's hard, okay? Let's not do that. Okay, good. Now, this is the definition of the cluster category. This definition of the cluster category has been given in 2006 by Buranmar, Reinecke, Reiten, and Todorov. And then they proved a number of results. So um, this is the main theorem coming from representation theory. Yeah. Give me a second. I see there are some questions in the chat. So first about no oriented cycle means that we do not have a cycle of arrows that gives rise to an oriented path. So this is an oriented cycle, and I do not allow oriented cycles. Okay? And the second question, the knitting algorithm for cluster variable is not special for type A. I can do it always. I could do, where do I have some space? Okay. Did we do type D somewhere? So nothing
Yesterday,
of what we,
tutorial.
huh?
Tutorial we did, type D.
Yeah, I mean we looked at a quiver of type D, say like so, yeah. And I can do the same game. I can compute the Z Q, and I fill the ZQ by arrows in the reverse direction. and so on. So I can compute ZQ, and then I can perform the exact same algorithm. Suppose I put my cluster variables x1, x2, x3, x4 here. These are the initial variables. And then I would compute the cluster variable x1 prime by exactly the same formula. Yeah, x prime is 1 plus the product 1 plus x2 divided by x1. So this is how I compute x1 prime. How do I compute this cluster variable? It's 1 plus the product of these three divided by tau of it. The same formula applies. Yeah, this is totally independent of the type. It works always. You can do type E8 if you wish. It's going to be complicated, but it works. You can even do non-Dynkin types. It works also for non-Dynkin types. It works for any quiver that has no oriented cycles. This algorithm works, and it will produce cluster variables. That's good. Okay, so here's the theorem. We defined the cluster category by identifying the action of tau and the shift. And here's the theorem Buan-Marsh, Reinecke, Reiten-Todorf, 2006. Let me first start with the Dynkin quiver because there's everything finite and we can say more, we get better results. So first, in that case of a Dynkin quiver, there's now a bijection between the indecomposable objects in the cluster category and the cluster variables. Yeah, this cluster category contains these copies of the projectives, the shift of the projectives. They correspond to the initial cluster variables. And then there are the others, the non-initial cluster variables, and they correspond to indecomposables, to indecomposable representations of the quiver Q. Yeah, so this is what we observed here. We have one copy of the projective shift by one, and then we have the non-initial cluster variables correspond to the representations. B, under this bijection, so now we go into the question, how can we characterize the clusters? And we have to spend more time on this. Yeah. So B, under that bijection, the clusters, so remember cluster variables are grouped into clusters in the cluster algebra combinatorics. The clusters correspond to cluster tilting sets. Okay, what is a cluster tilting set? So these are sets of indecomposable objects, T1 to Tn, in the cluster category, such that x1 from Ti to Tj is 0 for any I and j. So I'm aware that I did not define x1. I will come back to this. This is just, I want to state their theorem in one, so this is the main theorem, and then we need to work on it.
I did define it.
You did explain, you did verify,
Thomas,
you did
yeah,
define
I
x1,
did.
yes.
I did
Okay.
both the definitions. Yeah.
Okay, good. Thank
And
you very much.
do you also need that X1 Ti is zero?
Excuse me?
Do you also need that X1 Ti is 0?
Yes.
Yeah, like rigidity.
Okay, thanks.
Rigidity composition.
Yeah. So I say here this holds for all I and j, so they could be, in particular, they could be equal. Yeah.
I think even in the previous case, like in the case A, you need rigid indecomposables of CQ.
Yes. Yes.
Like fixed of T. Yeah.
Yeah. So this is for, so it could be that I is equal to j, then x ti is 0. And also, if I is different from j, there's no extensions. That's what that I need that, yes. And the last part is when I have a seed, so a seed is given by a quiver denoted R and a cluster U, then the question is, how can I recover? So say I understand totally this cluster category. I understand the indecomposables correspond to cluster variables. I understand now the clusters. These are certain collections of indecomposables satisfying some condition. So I do have a cluster. So if I have such a cluster tilting set, this corresponds to the U. How do I find the quiver R? Yeah. How can I go back to the cluster algebra and compute this quiver? And the answer is that the quiver of the seed that is giving rise to of the seed containing U, so this cluster tilting Z, the quiver is equal to the quiver of the endomorphism ring of that object. Yeah. So I have these T1 plus Tn. I take its endomorphism ring. This is a certain ring. And that algebra has a quiver. And this is the quiver R that gives me the seed. So the cluster here determines the quiver in that way. Yeah, if I have a cluster tilting set, I compute its endomorphism algebra, I compute the quiver of it, and I do get that's the quiver that corresponds to the quiver in that seed. Okay, so I want to illustrate those results. First,
Sorry to
yeah,
interrupt you, Thomas. Before you go forward, you said that the knitting process it works for all quivers,
yeah.
all acyclic quivers. Like for example, for Kronecker, you can't embed the model category into the repetitive quiver, right? Ah,
Hubble's theorem here fails, yeah.
no. So I mean, I know you take the copy of the model category and you add the shifted projectors, but then it doesn't come through the theory of repetitive quivers, I believe.
Yes.
Mhm.
The Hubble's theorem of repetitive quivers only works for the Dünken quivers.
Mhm.
And
Yeah.
the derived category in general is still made of shifts of the category of representations. The knitting algorithm even works also in the infinite case. However, you will not
Get
produce
all the
necessarily
cluster
all.
variables. Mhm.
Yeah, I mean, first, it never ends. I mean,
Yeah. Yeah.
you can start knitting and you will never end. Yeah, so this is
Mhm.
already a bad start.
Uh-huh.
So the good case is when we are in the Dünken case, then the knitting procedure stops. In the sense we do come back to the initial cluster variables.
Okay.
If you have a
Nice.
non-Dünken quiver, you can start knitting. You produce many cluster variables, but it never stops,
Okay.
and you will
And
not find.
you don't get all of them. Mhm.
You don't get all of them either. Yes.
Okay. Thank you.
Yep. Thank you. Yeah, this is good.
And if you have a
Um,
finite representation type
yeah.
algebra, then what kind of shapes can one expect? Like, let's say take an and put just one relation.
Yeah.
So what kind of shapes do you expect for this new quiver?
I'm not sure if I understand your question totally.
So I'm saying that if you just take one copy of an, let's say,
Yeah.
and
Yeah.
put one relation,
Okay.
yeah, let's say A3, and then declare that
Yes. Yes. Yes.
alpha
Yes. Yes.
beta
Yes.
is
Yes. Yes.
0.
Yes. Yes. Yes.
Yeah,
Yes.
then
Yes.
do you still get the same thing? Because you just answered to Isha that for infinite representation type, that won't work. But for finite representation type,
It doesn't work either. Like the derived
I
category can have a very weird shape.
at this moment
Or
I consider only quivers, no
only quivers.
relations.
Okay, okay.
Yeah.
Thanks.
If you start doing quivers with relations, then the derived category is getting a lot more complicated.
Right.
And the theory as presented here does not apply.
Okay,
Yeah.
thanks.
Yeah. Thank you. So at this moment, this is really for quivers. the particular result about this bijection is for Dünkin quivers. Yeah. So
yeah, I
yes.
believe you also need the object T to be basic. Like all the TIs should come with one multiplicity. Or
Yes.
object.
Yeah. I forgot that here. I need to add that Ti is non-isomorphic to Tj for I different J. Yes, thank you very much. This one?
Yes.
Yes. Yeah, sorry.
And also the category is Schmidt, right? You were talking about endomorphism. So anyway.
The category is cluster category. Yes, this is a nice Kohl-Schmidt category. It's sufficient if we specify the indecomposables, and then every object will be given uniquely as a direct sum of indecomposables. Yes.
Yes, thank
So just one piece of notation. The endomorphism ring of such a cluster tilting set, this is called a cluster tilted algebra. Yeah, I will come back to this. Okay, so I feel we need some explanation on going about that theorem. So first, we said that the knitting algorithm is compatible. I mean, that's what we explained. The definition, the motivation to define the cluster category as we did comes from this knitting algorithm. And knitting variables or knitting representations goes in the same way. And that's how you prove the theorem. For part B, Amit, now I'm cheating. I'm using the Ausländerreiten formula, which allows me to translate the definition of X1 into the definition of some homomorphism. Yeah. So that's what I'm using for today. Yeah. There's a formula, Ausländerreiten formula, which you mentioned, I think, last week. Did you?
Yeah, I gave a proof
Yeah.
as well. Yeah, short proof.
Okay, this is perfect. And in the Ausländerreiten formula, you have to consider the stable hom. I forgot, either it is the stable hom here or here. However, if I am in a hereditary category, if I consider representations of a quiver without relations, I can forget about the stable. And I really have that x1 between these two objects is zero if and only if there are no morphisms from Tj into tau of Ti. So I need to reverse the order here. Ti to Tj goes to Tj to tau Ti. But this is really how I can control the x1. I can compute x1 like this. Yeah. And I want to run some examples, and I will use that formula to compute x1. Yeah, so that definition, we translate it like that. That's okay? And for the last part, what is the quiver of the endomorphism ring? This is also something that Amit did. We have Gabriel's theorem. The endomorphism ring is a finite dimensional algebra. The finite dimensional algebra, any finite dimensional algebra, can be written as a quiver with relation by an admissible ideal. So what is the quiver of this one? Yeah, you go use Gabriel's theorem. This algebra comes with a quiver. That's what we are talking about. This is the quiver we are talking about. Okay. Good. Okay, so this is fine. Uh, this is the main result that people came up with, and I want to do a couple of things before I go into cluster tilting theory. I wanted to quickly talk about tilting theory. Let's go back to the basics. Yeah, so this is one thing that I want to do, and then I want to illustrate all these results by some examples. Okay, good. So before we talk about cluster tilted algebras and cluster tilting sets, the whole notation is motivated by tilted algebras and tilting modules. So let's go back to the to the 80s, to the 1980s, where tilting theory was one of the hot topics in representation theory. Yeah. So by the way, in the early 2000s, cluster tilting and cluster categories, cluster theory has been replacing tilting theory as the hot topic, as the thing that you want to do. So in 2005, in 2010, if you were a young researcher or if a professor had a PhD student, they would give them some question in cluster theory. Yeah. And these were the early days. There were many, Fomin and Zeliwinski, they formulated tons of conjectures. They had many concepts of certain polynomials, F polynomials, G vectors, C vectors, and many conjectures about them. And you could sit down using representation theory and slowly solve some of these conjectures. So these were the early, the easy days, yeah. And I was part of this. I profited from the situation. And nowadays, cluster theory is like 25 years old. If you want to still advance the theory, you have to go really deep. You have to do maybe quantum cluster algebras. You have to go deep into the theory. It's getting hard. Yeah, what I want to say, in the beginning, when the theory takes off, there's many questions that can be solved, which are accessible. But by now, how you say this in English? The low-hanging fruit have been picked. Yeah. And if I have a new PhD student, I would not necessarily give them a question on cluster theory because it's hard to advance. Yeah. It's a mature theory by now. Okay, sorry, this was a little remark. So let's go back to the 1980s, tilting theory. I go over this very quickly. So I have a finite dimensional algebra. A module over this algebra is called a tilting module if it satisfies three conditions. First condition, it should have projective dimension at most one. Second requirement, it should be rigid. This means x1 of tt equals 0. And third condition is it's kind of large enough. The additive hull of t, so is large enough to embed the original algebra, to find the original algebra as a kernel of two maps between copies of T. So that's the original definition of a tilting module. When we consider the past algebra of a quiver, as we do here, I only consider quivers, no relations, then those conditions become kind of easier. First thing, the projective dimension is always bounded by 1 because this is a hereditary category. So I can completely delete this condition. And I find that a module, a representation over Q is a tilting module if and only if, still being rigid, has no self-extensions. And the second condition can be reformulated. The third condition can be reformulated in the following way. It is the largest possible rigid module. So if I write my module T as a sum of n indecomposable objects which are pairwise non-isomorphic, then this number n is the number of vertices in the quiver. Yeah. And note that whenever I have a module which is rigid and I write it as a sum of R non-isomorphic indecomposables, then this number R is bounded by n. So n is the maximum possible value here. And if I reach this maximum possible value, then I satisfy that property that I have over here. So tilting, you can say, is a maximal rigid module. It's a module that is rigid, has no self-extensions, and it has the maximum number of summons. This is a tilting module. That's okay? Good. And in that case, the endomorphism ring of this algebra is called a tilted algebra. And there is the classical theorem by Butler and Brenner, which I will not go much into detail. And I can now try to compare modules over the original algebra with modules over this tilted algebra, the endomorphism ring B, by the functor hom t blank. So if I do hom t into some module, into some lambda module, this inherits the structure of a module. And that functor has nice properties in terms of the module category. I can identify a certain subcategory which is isomorphic to another subcategory of mod B. So I can identify some subcategory of the original algebra with a certain subcategory of the tilted algebra. And this identification is even more beautiful in terms of the derived categories. They become equivalent, and the Grothendieck groups are also equivalent under this same functor. So this is a nice theory that allows us to identify derived categories and certain parts of the module categories. So this is the classical tilting theory. I will not go more into detail of this one. What I want to do now is do some examples of tilting. Okay, so let's take an example quiver type AN. I could do any DN E6 or any quiver. I would like to do it for AN, but I like to take a large enough AN so we see a little bit some more interesting examples. Okay. Okay. So to understand the tilting condition, we said that there should be no extensions between the different summands, but that we can control by saying the homomorphism between one summand and the tau of another summand should be 0. Yeah. So first thing first, we need to understand the homomorphisms. Yeah. So let's do that. We want to understand what are the morphisms in that category. So if I give myself a quiver of type A5, it has the Ausländerreiten quiver has this shape. Yeah, I don't even specify the dimension vectors. This is really not of importance. That's the shape of the Ausländerreiten quivers. All the indecomposable modules are described here, and all their morphisms are described here because these are the irreducible morphisms, and every morphism is going to be a composition of those. Yeah. So if I want to understand hom of some object, so now if I want to create some, if I want to find some tilting modules, I will choose one indecomposable, say this one. I look into this, so say this is going to be my one summon tj, and then I want to control, first let's try to understand where does tj map. Yeah, so what are the non-zero morphisms from tj in that shape of the Ausländerreiten quiver? So what I can observe is that TJ maps to itself. There's a morphism into here, there's a morphism into there. There's another morphism into here, but along that dashed line, I have commutativity. So there's the morphism space is one-dimensional from TJ into this module, into that, into this, and into this module. And in the same way, I can go down here, I can go down here. So these are exactly the objects X where there's a one-dimensional morphism space from Tj into X, and everywhere else there are no morphisms. So this is the picture. Yeah. Why is there no morphism down here? The morphism would factor through this one, but if I factor through such a relation here, this is a zero relation, there is no morphism from here between these two. Yeah. So I can compute, I can understand.
Sorry,
Yeah.
sorry. So yeah. So what is the underlying category? Is it the derived category or the representation
In
category?
in this moment, I only look at representations of Q. So I do
Okay.
classical tilting theory. I only look at rep Q. This is the category of representations of Q. Just basic representation theory of quivers. Okay.
Thank you.
Good. And I just want to understand what is the shape of the morphisms. So morphisms from here are one-dimensional there, and they are zero everywhere else. That's all. I want to build up some understanding. How can I choose tilting modules? Tilting modules are the choice of a certain set of indecomposables. How can I choose them such that they do not, such that they are rigid modules? Okay. So for the rigidity, I'm interested in that thing, this hom tj tau x, because as we said, this is going to be isomorphic to x1 x tau tj. And this is the thing that we want to control. We want the x1 to be 0. So we want this hom tj into tau x to be 0. So if I understand the morphisms up here, then I just need to shift that rectangle by tau. I shift that rectangle by tau over here, and then I understand what is hom from tj into tau x. Yeah. So the shift of this rectangle survives only on this part. And I see that the dimension from tau j to tau x is 1, precisely when I have an object x here or here or here. And in all other cases, it is 0. Yeah. So that means, suppose I want to define a tilting module. I pick some indecomposable objects. Say I pick this tj, which you see here in light blue. Yeah. tj is only one summand. For a tilting object, I need to pick 5 summonds, so I need to make more choices, yeah? So for my second summand, I could pick any place here, 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 there. All those are valid choices for a second summon ti, such that there is no extension between ti and tj. I got plenty of space. That's good? Okay. So I did some pick already. I picked an example of a tilting module, so I stick with my first choice here in the middle. This was our TJ, and then I can pick a second summon, say T2 here. The second summon, I always have to control uh, hom of the summoned into tau of somebody. So this has a hom set, a non-trivial hom set here. Then I shift this by tau. This is a non-trivial hom set here. So this is the part that I kind of have to avoid. Yeah, if I pick T2, I have to avoid this violet region. Yeah, but I can continue picking other modules. So T1, T2, I can continue picking T3 here. This is in the valid region. This avoids all that set where hom tj tau x would be non-zero. So this is a valid choice. I can pick one here. I can pick T5 here. So these 5 indecomposables, they form a tilting module. So do you see a little bit what we are doing here? What we are doing here, I mean, we start with the representation, with the Ausländerreiten quiver, and then we want to pick a tilting module, and it's really, if our quiver has 5 vertices like so, we really have to pick 5 indecomposables. I could pick, I don't know, this one, that one, and so they don't extend. I mean, you compute where are the sets of homomorphisms. So the first one has a homomorphism here. So it has a homomorphism to tau of it here. I have to avoid this region. Yeah. The second one has morphism to that region, but tau of this is outside of the category, so no condition here. This has morphism only to itself. Tau of it is outside here, so there's no condition. So if I want to continue these three, I can choose everywhere in that region. Yeah. To have a tilting module, I need 5. I have got only 3, so I will choose anyone in the remaining region. Do you have any suggestions? Where would I pick? This is a game you can do. This is a puzzle, a game. Where would you pick? Do you have any preferred place? Do you have some suggestions on the left-hand rim or on the lower part where you prefer?
One on left, one on the lower part.
Okay, so let's do one on the left. Which one on the left do you want? 1, 2, 3? You pick.
Second.
Okay, so I choose this one. That's good. If I choose this one, I have to control the morphisms. So morphisms are in that region. Yeah. The shift of that region, tau of that region is this one. So this is the region that I have to avoid. Good. So let's color this. I have to avoid that region. So these are out of the picture. I cannot choose anyone here. Yeah. So you gave me a difficult task. I want to pick one in the lower part, but the pick here made me, I cannot choose anyone here. Yeah, so there's only one choice left. I pick this one. That's good? Okay, good. Then I have how many summons? 1, 2, 3, 4, 5. Yes, that works. This is a tilting module. This is how it works. That's good? Okay. So this is a game that we can do. So this the blue okay, what did I do? Sorry. Sorry, here. Yeah, I'm good. So the blue choices would correspond to a tilting module. Okay, now further down, I picked myself another tilting module given by these 5 objects, T1, 2, 3, 4, 5. And I can check by hand that this is a tilting module. Then what is this tilted algebra? The tilted algebra is given by the endomorphism ring. So between those summons here, I can check what are the morphisms. So there's a morphism from 4 to 5, one from 1 to 5, one from 2 to 1, one from 1 to 3. So the endomorphism algebra is really given by these morphisms from 4 to 5, 1 to 5, 2 to 1, and 1 to 3. And I do see when I compose these two morphisms, I go through the zero relations at the bottom here, so there would be a zero relation here. I really see, I can read off the endomorphism ring from that picture. This is the endomorphism ring. Do you see that? And just for the fun of it, I can compute the endomorphism ring of Riju's example. Do you want me to do that? Up here, so this one was our choice of a tilting module. The endomorphism ring, this is a tilting module T. The endomorphism ring of T this time would be given by seemingly such line. So there's a morphism from here to here to here. This is what I have there. And then there's a morphism down there. So there's a morphism down there. But that morphism here goes through a zero relation. So I do have a zero relation there. And what else? There's a morphism from here to here. There's a morphism from here to here. That's all. That's it, right?
There should
There's a
be one more
morphism.
relation.
There should be one more relation. If I start here, I go up there and I go down there. This is commutes. This goes through the zero relations. So there must be a zero relation like this. That's good? Yeah. So computing these tilted algebras is not so complicated. You just look at your quiver. Where are the summons of the tilting module placed, and you just look where are the morphisms going. Yeah. And that whole thing is done easily in type AN, but if you have our type DN or other Dynkin types, you could still do it. Yeah, I mean, in this case, the calculation of the morphism spaces is a bit more complicated, but you could still pick some indecomposables, and you just need to verify that there's no morphisms between them and tau of the others. Yeah, so you can do the same game. This does not depend. My example is kind of easier for type A. That's why I pick type A, but you can do this in principle for other Dynkin types or for other quivers. Yeah. So this is our tilted algebra. Good. Now there's classical tilting theory. This is Hubble's completion theorem. Yeah, Hubble says when I have a rigid module X that has one summand less. So I have a rigid module that has n minus one summonds. We do know that a tilting module has n summonds. So can I complete such a rigid module? Can I complete it to a tilting module? Yeah, can I add one summand in such a way that the whole thing becomes a tilting module? And then Hubble showed in the 80s such what he called an almost tilting module that can be completed to a tilting module, and there are in fact at most two such completions possible. So I get a tilting module T by adding a summoned number n to this X, and maybe there's at most two, maybe there's another way to complete it to a tilting module by adding another summand Tn prime. Yeah. Now let's relate this to our cluster theory. In cluster algebras, when we are given a cluster, we want to define a mutation of the cluster. A mutation would take one cluster variable and replace it by another cluster variable. In our picture of the cluster category, this should be corresponding to I choose a cluster tilting set. I want to remove one summand and replace it by another summand, so this thing becomes again a cluster tilting set. Yeah, we have a similar situation here. If I have that tilting set, tilting module, or that tilting module, what I could do is, sorry, I made a mistake here. What I could do is the following. I could consider that T, and I could define a mutation of T as follows. I remove um, the summoned number T, and I replace it by the summoned Tn prime. Sorry, say this T is my tilting module given by x plus one summand Tn. So the mutation would be the following. I remove that summand and I replace it by this other possible completion. So whenever I have n minus one summonds and there's two ways to complete them, then I can interpret this. This gives rise to a mutation. I can mutate one Tn by Tn prime. That's good. However, Hubble does not guarantee there's always two completions. There might be only one completion. So if there's only one completion, then we cannot mutate that one summand. Yeah. You can remove it, but there's only one unique way to put it in back in. I cannot exchange it to another summand. So tilting theory is almost good. This is almost what we want in cluster theory. In many cases, a mutation is defined, but not quite always. Sometimes it doesn't work. Okay. So in our example, let's do some examples. So in our example, our tilting module is given by T1, 2, 3, 4, 5. And say I want to mutate in 5. So I would like to remove the T5. I would like to remove this guy and replace it by somebody else such that the whole thing again is a tilting module. Yeah. And if you do the calculation, if you take out this one and you want to fill in somebody new instead of this one, you do see I cannot take anyone here because their home space would map into this one or no, into this one. I cannot take those. None of these is allowed. That's the only way you can fill it. Yeah. There's a unique summons, this T5 prime. And this is what Happel tells me in any case. If I have T1, T2, T3, and T4, there's at most two ways to fill it, T5 or T5 prime. There's no more possibilities. Yeah. So the exchange would be really exchange T5 to T5 prime. So this is my mutation. Yeah. So the mutation in 5 is possible. And the new tilted algebra. By now you're really good in computing tilted algebras, are you? What is the new tilted algebra? This is the algebra of morphisms between these guys. You see what I'm doing? Yeah. So that would be the new algebra, the new 5, the 5 prime maps into 1, 2 maps into here. This maps into 4. And 1 maps into 3, and there's a 0 relation. This is my tilted algebra, yeah? And if you look at it closely, that tilted algebra is really the reflection of the algebra that we had before. I mean, the algebra, where is my algebra? I lost my algebra. This is my algebra that I had before, yeah? I do see 5 is a sink. And if I apply the reflection at this sink, I would forget that arrow and I would introduce a new arrow over here. Yeah. So the sink turns into a source. So this is really how you compute the reflection, right? And that actually is what has happened here. Yeah. And you see it kind of in the Ausländerreiten quiver. So if I replace that summand here by the summand there, what happens? The 2 arrows going into 5 turn into 2 arrows that leave 5 prime. Yeah. So the mutation of the tilted algebra is really the reflection on that quiver. Yeah. So it works very well together. That's okay. You see that? Good. Uh, Then, but okay, so this works well. I can replace, I can mutate in 5, in 1, in 2, in 3. It works all very well. However, there's a problem with this guy. Yep. If I want to take out this one, so if I'm in my original, let's yeah, if you were to try to remove T4, and then you do the calculation, can I replace it by anybody here or there while keeping the others? And then you see it doesn't work. Yeah. That's summoned here, and for the expert, this is a projective injective module. Projective injective modules have to be present always in any tilting module. You cannot mutate this one. Yeah, you can play the game and try to remove it and see is there any other valid candidate, and you will see you don't find anyone. So this one has no other completion than by T4 itself. You cannot mutate T4. So that's not good. Because in cluster theory, we want to be able to always mutate any summand. However, this one cannot be mutated. Yeah. So for this reason, we need kind of enlarge our category in order to be able to mutate that guy. Yeah. And that is really the step going from tilting to cluster tilting. Yeah. Cluster tilting is in a larger category, and this will create a space that we can mutate any summand. Yeah. So let's I've got a couple of minutes left. Is this correct? So in order to always be able to mutate, we have to find more space. Excuse me. We have to work in a larger category so that we do find another object that can play the role of the new object when we want to mutate. But I have got only 5 minutes. I don't think I really want to go into the cluster tilting story. I will do that tomorrow. Let me just finish off with the example. Let's do just one example. So I will do this tomorrow again, but just to address the question that we had. So I have my cluster tilting category for the same quiver of type A5. Here's the same representations. Here's the same object. And we will find this is still a tilting object in that new category. And the only thing that we added here this left-hand part, which we identify with the right-hand part. We only add one line, really, okay? But adding this one line allows me, this time around, allows me to mutate T4. I can replace it by this summand. Yeah. So I just created a little more space. If I keep all the four others and I want to delete this one, there's a new possibility created, that one, which allows me to do a mutation. Yeah. So that's the basic idea of the cluster category. We create a little more space so we are able to mutate any summand always, because this is what cluster theory is about. A mutation is always possible. Yeah. And I want to address this, but I want not to rush this in the last 4 minutes, so I would like to do this tomorrow. Maybe if there's any question, you can address them now. Are there some open things, something that you would like to see in the following lectures? You can tell me.
A question.
Yeah.
So you calculated the endomorphism algebra of the tilting module, and then you calculated the endomorphism algebra of the mutation. And here they were
Yes.
related by this, like by the reflection. But is this general? Like the relation between the endomorphism algebra of the mutation. Mu5.
That works out pretty nicely, does it?
Yeah, here, but I
I'm I'm
like
I'm afraid it worked out nicely because it was an actual reflection.
yeah. Mhm.
And if you were to mutate, somewhere where there's a path of length 2 going through this vertex,
Mhm.
I do believe it would mess up the things.
Okay.
And it
Mhm.
would not work with the tilting theory. It would work for cluster tilting.
Yeah, yeah, okay. Mhm.
Yeah. So the cluster tilting mutation is made for this. It works well there. Yeah.
Mhm.
But yeah. You see what I mean? I mean, you cannot
Yeah,
mutate here because then
yeah,
that
I
is not
mean,
a
so
reflection anymore. Yeah.
like it was because I tried doing this for mu3 and it doesn't work. Like even for 3
Yes, yes,
because
yes,
then
yes.
the path coming in is actually part of a relation and
Yes, yes, yes,
yeah.
yes, yes,
Nah.
yes, yes, yes.
Mhm. Okay, thank
I
you.
I believe if we were doing it for the cluster tilted story, it would work.
Mhm. I see.
Yes, I have a question.
Yeah.
So Happel's result is in the derived category or Happel's completion?
No, this is in the module category.
It's only in the model category. But in the derived category, like the result for cluster category is like the cluster category is subcategory is the quotient of the derived category. So it like in the derived
Yes, yes,
category
yes, 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 yes.
you have the maps.
Uh,
Like you
so
like
so that whole section here was tilting theory, was classical module theory. We have modules over finite dimensional algebras. Okay.
I see.
Uh, and Happel's result tells us that there's at most two completion of a module that is rigid and it is missing just one summand. However, if you were in the derived category in D of Q, uh, you would always find like infinitely many. I mean, you find this and this and this and here. I mean, in the derived category, there's always infinitely many options that you can fill in, and you have a rigid object. So this is not what you want.
I see. And in the cluster category, you have exactly one. So it
In
it fits the
the cluster category which extends the module category by just adding just a copy of the projectives, there you create just enough space to add exactly one if needed. Yes.
I see.
If
Thank
you
you.
would do the derived category, you see what I want to say. I mean, you would kind of create infinitely many
Yes,
possibilities. Yeah. So that no, that's not what we want.
I see. But what was your comment in the last? Like you said that the object is projective, injective, and like generally people have extended it to Frobenius categories where in principle you may not be able to mutate at some vertex.
Yes, yes, yes. If you have a projective injective, you're not able to mutate this. Yeah.
I see.
But I mean, in Frobenius category, then you look at the stable category. I mean,
Yes,
you
yes,
quotient by the projective injectives, and in the stable category, you can mutate. Yeah, but just
yes,
before in the Frobenius, the projective injectives, you cannot mutate them. And if you know cluster algebras with frozen variables, they would correspond to frozen variables. These are exactly the objects that cannot be mutated.
yes, yes. And yeah, the projective injectives remains the same. Like that is also due to Happel, I
Yeah.
believe.
Yes. Yeah. Yeah. Yeah.
Okay. Okay. Thank you.
Thank you. Thank you.
Hopefully there will be more people. I'll make you a presenter.
Hello.
Hello?
I wasn't able to hear.
You were not able to hear yourself. Okay.
No, I wasn't able to hear you.